that I should repeat what I said last time in the hurry. I'm not sure. Yeah. When did I start with hurrying up? But yeah. So the mathematical fact which was used is the structure of Lagrangian algebras and products. Which is very restrictive. So the first step is to single out maximal subalgebras sitting in the factors. Maybe just call factors left and right, and then there are this two étale subalgebras. Which allow us to condense these categories down to places where these algebras will become analytical units, and then under this assumption, the modular invariant has to be a permutation type, and that was turned into fact. So get this.
So that was separable in particular, yeah. That was separable.
Étale in particular is separable, yes. So the sort of general statement that modular invariant is in one-to-one correspondence with this collection of two étale algebras, and then Riemann anti-equivalence, or rather an equivalence. With the Austrian structure, and then brought back to the language of CFTs. It says that in the CFT, when we start with a full space and then we single out two vertex separator subalgebras collecting all holomorphic and anti-holomorphic fields in them. Then if it is a rational case, then the modular invariant has to be permutations. So the only permutation modular invariants are possible. And yeah, that was surprising to realize, but in retrospect, we see this non-permutation modular invariance. We see this arbitrary case when we start with not just full holomorphic and anti-holomorphic subvalues, but we construct starting with say affine. And then there was a request last time, I think Azad was requesting to produce an example of something like that, where this holomorphic and anti-holomorphic are not the same VOA, are not isomorphic as VOAs. So example which is not meromorphic itself. And it seems to be traditional to use 1/2 central charge, Grasora minimal models, so that's what I will use. So if you start with this, and then, yeah, there are infinitely many affine VOAs with this very same representation category. And so that will be the smallest, but one of the examples is B rank 16 level 2. It will have the same representation category, so these two will be either categorical. And the central charges, no surprise, differ by a multiple of 8. And if you remember the formulas, you can tell me what the multiple is. But if not, yeah, so the difference is 16. And so to make them, oh yeah, I forgot to say the formulation. Algebraic description of rational. So there are two vertex-centered algebras, which are categorical. But yeah, plus this manifestation of this Isaac category. So maybe I won't say that. But yeah, they're of the same central charge. That is the condition which is important for canceling the global anomalies, and then yeah, the choice of equivalence, which gives us this permutation module invariant, but actually gives us more, gives us OPE, gives us the algebra structure, gives us the algebra structure here, which encodes the product expansion of all fields. So this information is important. And yeah, and then that's how we construct it. So here the central charges don't match, but they differ by 16. And so if we take a product with two copies of E8.
F is like a structure, or is just
F is a structure. Yes, right? The monodal structure, the ribbon monodal structure, ribbon grid, the structure of that translates into the algebra structure of this object. And the algebra structure of this object is what encodes how the OPEs are working in general. Well, not necessarily holomorphic and anti-holomorphic. So that shows it. And then these two will be just fine to be left and right. Holomorphic and anti-holomorphic. And then, yeah, they're not themselves holomorphic. The representation categories are easy. But yeah, it's sort of the general method, right? You just take two which are isocategorical, and then the central charges will differ by a multiple of 8. So you just stack this collection of E8s on one side to balance it up, and then
they're holomorphic, right?
Yeah, so these are holomorphic. These don't change representation category.
Maybe you can find some internal algebras in Web P16 too, so you get Web P12 too as local modules.
No, they're not condensations of each other, because they already have the same representation category, so they're not really related by conformal embeddings. They just have the same category of representations, and so are these two.
So it's braided tensor.
Yeah, it's just
braided tensor.
ribbon even. Yeah, ribbon.
So it's the second example, the next slide.
Yeah, so this extra piece is not changing the category.
Right.
We still have this equivalence. Choose it.
I think the question was
But
that
there's not much of a choice. There's no out equivalences of these.
too much central charges. Right?
Yeah, so these two are either categorical, but this condition of fixing,
Central charge.
and to make it work, we just we always have a fix. So the more standard fix, just
As a view, it's
start
very
on one
different.
side some number of copies of E8 level 1.
Then maybe the question, what are model invariants? Like you say.
So there is only one modular invariant here.
Oh.
There's only one modular invariant because there is no, so the freedom is how many ribbon out equivalences we have on either of these ends. And for Easing does none. So there's only unique. Full theory. With these two sectors. And then
you were saying model invariants are in bijection with Étale algebras and equivalences. So you're saying there are not so many
invariant side bijection with Lagrangian algebras.
Again?
So yeah, full CFTs are algebraically these gadgets, Lagrangian algebras. And then analyzing Lagrange algebras categorically, we see this data. So we see these two algebras, two Ital algebras, and then ribbon equivalents like that. So I think the first who realized that was Michael Milger. Some people came to that independently. The first who recorded it and published. So yeah, that description suggests so some operation. Why we can always swap. So if we have our CFTs written in this way, but there is an involution on a set of our CFTs, which I just changes. Oh no, this is inverse, quasi-inverse. The data will still be acceptable. But yeah, it seems that this operation can be seen on the level of just conformal field theories without any rational condition. This operation consists in taking a conformal field theory and sort of changing the complex structure. The complex structure is on all the surfaces, which we use to define correlators. And then the system of correlators is just the same, but we assign it to a conformal to a complex structure, which is the opposite to the original one. So like you see the operation, but that's what it does exactly that. And so it makes sense for all conformal theories. That was the first observation, but then I was really rushing through boundary. And what happens in the boundary, then left and right sectors will have to be the same. Yeah, Katrina was saying that they have to be isomorphic, and she was right, of course. So even yeah, in the field expressions, you still have this possibility of this. And then the sort of the boundary data for compatible boundary data, compatible boundary conditions. Form a category. Which has natural structure of module category of the representations of this. So yeah, if you look at the first, probably one of the first people who started analyzing boundary conformal field theory was Cardy, and then he was really playing with like two ways of making finite cylinder and putting two boundary conditions on the ends and originates in two ways. You could look at it progressing this way or progressing this way. And then from this interplay, he was deducing some relations. In particular, he was seeing this state spaces for these configurations as modules over of the chiral algebra. And that's what makes it a module category, because these are just A and B are simple objects in the category, and this is just the internal form. this is a somewhat non-standard way of describing
In this case,
module category
for
structure.
each edge A and B, he associate a
Which
representation of EOA,
which boundary
and it's just
condition?
A star B, right?
Yeah,
A star
so
tensor B.
yeah,
Makes
so-
like,
so
like a
yeah,
fusion. He defined
Yeah,
fusion.
yeah, you could make it an object by inserting a field in the middle of this. And then yeah, collecting the sort of the decomposition numbers brought this numerical integer matrix representations. And IAMs were sort of the gadget of the beginning of the story, but then people realized, and particularly in Hamburg, realized that this is just a model category. But yeah, in Hamburg they were really using algebra representations. So we're really talking in terms of Frobenius algebra, special Frobenius of boundary fields. But yeah, this is an alternative way. And then yeah, so Hamburg people and independently ENO proved this boundary bulk correspondence. So yeah, this category is special. Also, it is simple as a module and semi-simple So finally, I'm starting to approach full center construction. So that is this boundary bulk correspondence in the rational case, which says that if you look at equivalence classes, if you like, of this simple C module categories, it sort of again was observed in examples and computations and complete computations, like in the group theoretical case, where you have abundance of such things. So if C is the modular category corresponding, say, to a group and a Flickr cycle, it's twisted some. Only care about the terminology class, and then this simple module categories were classified by Ostrich, and the sort of the labels are subgroups, and then trivialization. So subgroups, sorry, of the product, and then. No, the group, and then a trivialization of the restriction.
Is it not for big G? Is it not for big G classification? So there is something.
Right. Sorry. Yeah. These are for big G. So these are
for big G with right?
Yeah. This is not quite fitable, but nevertheless. So yeah, these are for for vec G. But yeah, on the other side, we will have Lagrangian algebras in the, so maybe I'll call it differently, not C, but because C was a modular tensor category, maybe something else.
But for some cocycles, it might be modular, right? For some abelian cocycles, it's modular.
No, yeah, no, that is irrelevant. That is, yeah, okay, that is like first a generalization of this boundary bulk correspondence, which goes beyond just modular categories and beyond braided. So this is not braided at all, but so on this side we'll just have Lagrangian algebras in the center. So this is S now, and then C appears as a center. This was about 3. And then it's the same data. It's the same data, and then soon there are other examples. So that is one-to-one correspondence. But yeah, the same data for this particular example, but then people proved it for so any fusion.
I see.
But yeah.
So S doesn't need to be. That's just monoidal.
It's just fusion.
Just fusion, right? Okay. There is such correspondence.
There is such correspondence, yeah. And so when S is modular, that was common Runkel, and then in general, perhaps you can go for Fuchs in one of the books. Maybe we pay confusion. So in particular, when S is C modular, it gives so this boundary bulk correspondence. So for any boundary conditions we might have, we have a unique description of the bulk. We have a unique modular invariant. So any C-module, simple C-module will give us a unique Lagrangian algebra in the center. And the center that was observed by Michael Milger can be written as a product of 2 copies of the original category and its mirror version, recovering this holomorphic factorization. And this factorization is sort of nice. The functor going this way is sort of nice. You could call it like prototypical alpha induction. But yeah, that is just taking an object and making a half Bredian out of the Bredian or out of the inverse Bredian. And in the non-degenerate case, the intersection sort of is the symmetric center. And in non-degenerate case, you have a functor like that. And it's actually an equivalence, but yeah, Milger just looked at centralizes, Bredian centralizes. So Bredian centralizes of this is naturally that, and then he proved this factorization for just Bredian centralizes in general. And yeah, that is this boundary bulk correspondence, and that is what Fjellstad, Fuchs, Runkel and Schweigert called full center. And they have a formula, so their definition was somewhat interesting. So you're supposed to look at the monoidal factor, which is just the tensor product. Since C is braided, it is monoidal, and then doesn't matter left or right. I think the right is the correct one. Adjoint has to be used, and then the value on the identity. So maybe tensor product, and this is the adjoint, and then the value on the identity is in algebra in here. And then this full center is the left center of the, so to write the answer, one has to choose an algebra behind this module category. So choose some, maybe some algebra B in the C, and that B has to be separable. And haploid, or what's called, yeah, connected. And then you take this algebra object, you put it in one of the copies, this one, and then you take the tensor product with this R, and it's still an algebra by some conspiracy, and then you look at the sort of left center. And what Christoph was saying about during the Lucas's talk, so in your talk you had this two-stage constructions. You had the B, which one was the final B naught, right?
B naught first.
Oh, B naught first. So Christoph was suggesting that this is B naught, and then to get B, you have to sort of the projection is the projection to the center, which you can have in the separable case. You could write this center as the image of a certain idempotent, which they did in this Fjellstad, Fuchs, Runkel and Schweigert paper. And
So what is CL?
CL is the sort of, now you look at it as a braided category, and then you if you have an algebra in that category, you could look at the two centers using original braiding and the reverse one, and these are these left and right centers. So you have to choose the correct one.
But you didn't define it yet.
Sorry,
You did not define.
okay, it's not hard to define. So at this stage you have an algebra. So this is an algebra in
Sorry,
in the
another
braided
question.
category.
CB is what? B equals B equals
So
CB.
yeah, you write your module category in terms of algebras. That's what.
Yeah, same
that's
B.
what
Okay, B is your
happens.
C module and B is your algebra.
Yeah, but no, they're different. This is script. This is great.
I don't see it.
No, I can't help it.
Can you choose different?
This is straight. This is an algebra, and this is curly.
Okay,
This is
right more
category.
curly. please.
Yes, they're different fonts.
Especially from the camera, it will not be even video. It will not be. It will be confusing.
Many
It is already
people are
confusing.
watching. So yeah, this is an algebra object. Let's see.
Look at modules.
Algebra
There are modules over
connected.
here.
Connected and separable. Or the terminology used in the original paper was symmetric special frequencies.
So could you alternatively also, because you could apply R to the algebra B directly. Is it the same? maybe?
Yes. Yeah, but yeah, I'm just bringing the original formula just for us to marvel.
Is it really R of B?
Yeah.
It's R of B. Okay.
Yes.
Oh.
That's right. So it's R of B, but again, it's an algebra.
So not R of B, T star of B, right? So it's T star
So
of B.
T
T star of B. That's right. So this is a T star of B, which is again an algebra, but it's not a commutative algebra. And so if we have this is straight, we have now have to remember that we are sitting in a braided category.
Yeah.
And then we have an algebra. I used R, so I don't know what to do. In the braided category, we can construct two commutative algebras out of it by this so equalizer construction. So we have to equalize two morphisms, and one is this is an equalizer of what? Yeah. So how do I do that? I'm putting myself in the corner. Maybe I won't be able just to do it in a hurry. So the original again paper was to the original paper was producing it as the image of a certain idempotent. And yeah, will I be able to do this idempotent as well? But okay, so what is the idea? We have to look at the if we would have underlying vector spaces, we have to look at all the elements which would be commuting if they are sitting on the left or on the right. Am I saying it right? So yeah, with anything else. So this is CL. CL is CL of any algebra is that's supposed to be the same as this. So yeah, maybe not an equalizer, but as the term, as a terminal object among the pairs. So we just look at, so this is CL of something is terminal. Among the pairs, and we look at an object. I need more space. So
Are you defining left center or?
I'm defining left hand. Yes. So this there is a bracket category, and then there is an algebra here. Yes. So what is this left center of like this? That is terminal terminal object in following comma category. So we look at pairs, we look at object and the morphism into the algebra S. So it is going to be a subcategory in the comma category over S, and then we require that is a left central piece. So what does it mean? So we have X with S, and then we can think of it as sitting inside S, and then we will use multiplication S. But alternatively, we can swap using the grating. Again, think of this as a sitting inside S tensor S and do the multiplication. So that is the left version, and if we use the reverse braiding, we will have the right version, the right center. And in the original paper, that was defined as the image of a certain very cleverly designed idempotent, and that's what still be possible in this finite tensor case, and that's what Christoph was suspecting happening in your construction as well.
I mean, it does. I mean, there's also there's a definition of the center by an end over internal endotransformation.
Yes, that's what I'm coming.
And this is okay, because we know that agrees with that one. So if that one agrees
but that is this full center in so here a lot of specifics is used, the modularity in particular is for factorization and all that, but the full center appears already here, appears for fusion case, and actually just appears for just monoidal case as long as we have this terminal object existing. It's not even just full adjunction, but just like the identity. If we have them, we can so yeah, go in this way. This is general full center.
How do you define full center? Was not clear. You define left center and right center.
I'm coming to that.
Ah, okay, because
I'm just advertising, sort of motivating why we need it because yeah, it solves this problem. Yeah, so the construction, region construction was in terms of internal algebras, but then maybe Conan
That Z of B is called full center, right? Z of B.
Yeah,
It's about
but yeah, the Conan proved that it is Morita invariant as a construction. So it doesn't matter what the algebra is after Morita equivalence, it can give the same center. So I'm going to give this general definition. I'm going to give it in a way which is sort of makes it almost inevitable. And that is a good ground to believe that in other situations like finite or maybe infinite, semi-simple, or maybe just in general, it should be a good approximation of the full state space. But in some places, as Lucas is saying, is already proved. So you already know that you have this description in terms of the actual factor. And if you have it, then in particular, you don't need just have sort of projective. You can always compute how to, but yeah, I'm going to come. So what is the full center? Let's start again with this data of an algebra sitting in the monoidal category. So now it is just monoidal category. Forget all the adjectives. So what is its center? And there's no place for the center in the monoidal category. We can't really say what is to be commutative, but yeah, we could try to find the place in the monoidal center of the monoidal category. And then there is, so if you think in this way, there's a unique solution to that. And the definition is very much like over there is in terms of common category in terminal objects. But sort of it's a relative common category relative to the forgetful factor.
But it's the same you replace by half braiding?
Exactly. Yeah, so it's just to replace half braiding. That's it.
The terminal object in the Greenfield center.
Yeah, all right.
Object is half braiding.
In the category of pairs, where an object in the center, so I call it. That is an object in the center. It is an object in the category S, and it comes with a choice of half braiding. And then this is a comma bit. So interpreting it as a part of this algebra when you forget. And then, yeah, you draw the same type of diagram. So ignoring this forgetful thing, it's just in S, you have this diagram, the underlying object, the algebra B. And then the half braiding, which is part of this, so calling it little z. And if we have sorry, so yeah, it's again, it's defined in terms.
So Z is from f of z to b, right?
Sorry.
From f of z to b.
Yeah, so from the object underlying.
Yeah, but typo. It's no. On the after the arrow.
That's B. That's right. Sorry. It's slow. And yeah, okay, natural at all, but we really wanted to for module categories, but yeah, this construction is really for module categories because there is an analogous construction for module categories, which gives this answer if module category is a category of modules of some algebra, internal algebra. So if now it's this module, there is this nice easier formula which just says, okay, we have so the action of S on M leads to a central functor into dual category it's called, but I'm not really fond of that name. And the category of C-modular and the functors. And that is sort of like a big alpha induction. And then you take the left adjoint, left or right adjoint, and then you compute the value at the identity. So this is E, maybe star center of M is the value of the identity functor, and it is a commutative algebra in the center. And if the module category is the category of modules over some algebra, then this full center will be just that thing. And if the category is if the little category it's called yes, and if the little category, if the category S is modular, we recover that formula. We recover that formula because yeah, upon identification of the center, that's the product. Maybe we call it C. We recover that formula.
That formula as a left center of that thing.
Yeah, the left
The formula, I
center
mean left center of that thing.
So yeah, it's sort of some requirement for having a joint or just this terminal object, not necessarily much. And then yeah, there are general formulas for, say, the case when it's knocking, when S is representations of some algebra or by algebra in general. And you're saying that yeah, I missed the works which had the same answer maybe on the order than I was computing them.
I think maybe around the same time.
2010.
They somehow really
2010.
yeah. Same time.
So yeah, internal algebra in this category would be H modular algebra. Possible to record as an H modular algebra, but yeah, you could do the comodular algebra in the same way. So you, an algebra in the category, let's call it B, H modular algebra. And then, well, relatively easy to use the answer for this full center of B. It's supposed to live in the monoidal center of S, which is the category of Yetta-Drinfeld modules. And as the underlying module, I think it's adequate to say what it is. So we take the smash product with H, and then we take the centralizer of B in it, and it has an H module action, and it has an H module coaction, which some formulas, which makes it a Greenfield module and also an algebra inside. And again, it doesn't care about much. It even works without. Maybe that is a straight. Maybe just algebra. Maybe there is some antipode somewhere. Yeah, I just don't remember. Yeah, I remember some antipodes drawing them. So maybe to be on the safe side, just pop algebra. But well, yeah, not much after that. Okay, back to what I was claiming about rational conformal field theories, right? So there was some group made out of that. So these bits are all gone. Maybe I won't. Okay. So because of the boundary bulk correspondence, it's also easy to say which rational conformal field theories. So rational conformal field theories, remember, they are now just pairs of two VOEs of the same central charge plus this manifestation of them being isocategorical. And what allows to find the sort of the compatible boundary. So the two VOEs will have to be the same. That's the Cardi's message, such as 3D, up to isomorphism. Well, we're looking at them up to isomorphism anyway. And then because of boundary bulk correspondence, anything will do. Because anything will be just giving us a modular invariant, and boundary bulk correspondence says that any modular invariant comes from a module category, comes from some boundary data. So that is it. And then it's kind of like natural to declare them trivial and see what happens afterwards. And of course the mathematical ways to introduce a certain equivalence relation on rational conformal field theories, under which boundary things will be all equivalent. But yeah, it can be done now, because all what is used here is this involution, and it works on just conformal field theories. So it can be done in this, sorry, in this generality. Now we say that two conformal field theories are equivalent, sort of boundary equivalent. This way, if we take one tensor product with these complex conjugate of the other, and we can put a boundary on it. And then there are two ingredients which are required to. So yeah, we could take the we could take the classes, but yeah, this is not quite an equivalence relation yet, right? So you could see that two properties, reflexivity and symmetry, are obvious, but yeah, even symmetry is not obvious. So just for one of these properties, you would need this statement, and I'll make it as conjectures in the general CFTs. So if you take on the whole CFT and you take its complex conjugate, you always has a boundary.
Is this equivalent on full CFTs?
Yeah.
Is this equivalent on full CFTs?
Full CFTs. So that is the first, which is yeah. How much time do I have?
Yeah, I mean,
5 minutes, but
Okay.
5, 10.
So yeah, that is the first a first necessary thing to make it an equivalence relation. But for transitivity, we'll have the following statement. We'll need the following statement. So we'll have like H written as a product of two CFTs, and then the whole thing has a boundary, and one of them has a boundary, so the other has to have a boundary. So H has boundary, or H and H1 boundary extension from that H2 should have boundary. So this is sort of gauging or cosetting boundary. And both are verifiable in rational case. Yeah, the conjecture is that they're true for all CFTs, but the problem is what is the definition to check this conjecture? One has to have a definition, and if there is a working definition, this conjecture can be checked. And after that, you do have an equivalence relation on a set of full CFTs, and then it becomes a group. For free, it becomes a group just because of this. So the inverse is just going to be this complex conjugate. And as I was saying, so that is true in the conformal of the theories. Sorry, the first is an easy exercise, but yeah, just what happens when we take the complex conjugate of this pair, left VOA, right VOA, and the equivalence, we just swap the VOAs and take the inverse equivalence. And then when we take the product, we're true in the first. So VL, VR, equivalence, product with the conjugate, which is VR, VL, inverse equivalence. But when we take the product, we'll have the same VOA, so it is boundarable. And the second one is more interesting because the second one would be saying what? So if you unpack it, you will be looking at.
Still, we left VR. They're not connected, right?
Yeah. So the mirror is just flipping.
No. For each tensor, just VL VR.
Yeah.
It's not connected.
So the tensor, yeah. I didn't write the formula for the tensor product, but if you have two triples like that, so VL, VR, F, and then VL prime, VR prime, F prime. You just tensor them component-wise, right? Because again, they're left holomorphic, anti-holomorphic in the tensor product.
No, I mean, you don't assume VL equal VR or isomorphic. You don't assume.
No.
They're not connected.
You don't. If you assume that will be boundary.
Yes. But
And that's what.
so in
makes
these equivalent relations, you don't assume HH prime boundarable, right?
No.
It's just any full
For
CFT.
any H, for any full CFT, if you take.
I see.
If you take the double, if you take the product of the CFT with its mirror image with the conjugate, that has to have boundary extension, whatever the definition of CFT you're using, and then this statement that you can form cosets, and that's what exactly you're doing in the rational case. So you're really forming cosets. To prove the second in the rational case, you just take you are in a situation where you have a sub VOA in the VOA. But really this VOA is a tensor product of this something and the something else. So the cancellation property for tensor products of VOAs. And it is manifested by the coset construction of Runkel and Schweigert. And so you have it this way. And that gives a group, and it's rather big group. But yeah, as I understand, it is not even known if this group is countable or not. So it is. I think it is believed that rational VOEs for any central charge is discrete for discrete families. But even for the monster, it could be a continuum of monsters. So no one really knows. Right? I don't think there's a statement to that effect. So yeah, even for rational, the group is rather mysterious, but maybe it is useful as an organizing tool, especially if it works for CFTs. For CFTs. So yeah, I think I'm running out of time.
Yeah, I think because we have second talk. You want to continue tomorrow? You said nothing about non-semi-simple.
But yeah, okay, yeah. So
or non-rational.
Yeah, this formula, for example, we could apply to any Hopf algebra, and yeah, but there are definite sort of departures from the otherwise beautiful case. So, for example, this, if it is so, if you so here it is modular fusion category MFC. But if what is modulates is essentially it is not degenerate. So the Riemann part is really detachable, decouplable. But essentially it's non-degenerate as braided category. And if you still keep semi-simple but make it like infinite, then this goes away. And the easiest example would be SL2, again, the standard example as usual, quantum SL2 at generic value of Q, or temporary category, if you like, at the generic Q. And that is no longer true. Kind of easy to see this one extra object, which is an invertible one of order 2. So for C representations of UQ, SL2, generic. Yeah, it's not so easy to compute the different modules, but this is still, as a braided category, is non-degenerate. The symmetric center is trivial, so we still have the two copies mapped into the center. But there's something else, and this something else sees modular invariance. So they're not really completely factorized.
What is this something else?
So something else, yeah, you have it all the time. So if you have monoidal automorphisms of the identity functor, or in other way, gradients of the category, you could turn them into central structures on the identity object. So it's actually just a complete description of central structures on the identity object. So possible central structures you can put here to make it an object in the center. They are monoidal automorphisms of the identity functor, deforming the standard central structure of the identity object, which makes the identity object in the center. You could do by taking any of those. And then for temporary, for this, the reason is Z2 gradient. So this group for that example is order 2. And then you have an invertible object in the center, and then you could see that if you have a module category which sort of splits into a direct sum of 2. Then you will make this act non-trivially on the module category, and then you will have this object sitting in the full center of that. So if now a C module,
You think this object has extensions with the other guys? It has extensions. Does it has extensions?
So this object self-extensions.
No, does it has extensions with the other guys? With the guys you can see?
Yeah, that's a good question. So I believe there should be extensions even in this semi-simple case in the temporary category, because yeah, the self-extensions of the identity of degree 3 should govern deformation theory, and there is interest in deformation theory of that. Definitely just going away from Q. So there should be 3 cycles, so there should be.
But the deformations are deformations of monoidal functor, right? Of monoidal structure. Here.
So yeah, deformations of this category will be visible as extensions in this category.
Yeah, I agree with you, but these deformations, are they of like, because I mean this result is for infinitesimal deformations of associators. Because if you want to describe all these Q as associators, it will be Dirichlet type associators, right? It's not infinitesimal.
That's the only thing you can deform. This is a simple category in generic Q. So you only deform in associators, and then you do have a deformation because
they are Dirichlet type associators.
So what does it mean, Dirichlet?
No, but they start with degree square, 1 plus h square plus.
No, it's only you're confusing yourself. It's only at the symmetric point.
Yes.
It's only when you try to get away from the symmetric point, you have to do that.
Yes,
because otherwise you will be creating something not braided and not fiberable.
Yes.
But in this case, no, it's all smooth.
If I sit at Q,
in the generic Q, it is smooth, and so you just deform it. You just add epsilon to Q, look at it over the whole numbers, and then you compare with this. Just stands it over with the whole numbers, and you have a 3 cycle, which has to be non-trivial. So that, yeah, it's everywhere smooth apart from the symmetric. The main point is indeed, as you say, is this Dirichlet thing. It has to be, so yeah, the actual direction is, the actual tangent is 0 for the Dirichlet associator, the first degree term.
But here not, if I sit at generic Q, then tangent space is not trivial.
Then the family becomes smooth. And that family is a good approximation of the modular space of the deformations of the category.
And
then this fact is just straightforward and easy to check. So what I'm saying is that what is the C module category? Because this is just temporary leap. This is C, but there is a better name. It's temporary leap. So this dimension which is negative U goes.
So, but Alexei, we have to stop. Do you want to continue tomorrow a bit?
No. It's just one thing. I'm saying that pathologies appear even in a semi-simple case. Simple but not finite. And the pathologist is like that. So it's not modular invariance for still reasonable. Maybe they're not reasonable, but yeah, you have to be careful with choosing the boundary data. So yeah, what is the module category over there? This is a freely generated by one self-dual object of that dimension D. And then module categories, again, is just functor. And you could imagine the self-adjoint functors with extra structured dimensions. And then you could just write M as a sum of 2 things. So M1 and M2. Constructing such self-adjoint functor, you can just take the 2 copies and then an adjunction between them, and the functor will be this off-diagonal sum of these adjunctions. And if you construct such example, then this outer equivalence, so this central object will see the full modular invariance. So the full center will have a non-zero form in the center from this into that. But that is not factorizable. So the full center is definitely not factorizable. So it picks up something funny. It's interesting. Yeah, it's all like all going to be interesting if we drop even finance. Thanks.
Thank you, Alexei. One quick question.
This equivalence with Lagrangian subalgebras of the center and simple or indecomposable modular categories. Do you know if this is also true for non-semi-simple modular category, maybe?
Like E star, I think this is
boundary bulk correspondence, right? Yes. Yeah. No.
I think the natural conjecture like E star of identity for any exact model category is a Lagrangian.
Yes, okay.
But
so yes,
was it
I did
proven?
say
Was it
that.
proven? I think I searched in literature. Was it proven for every finite tensor category? Huh? No. I mean, it's a question. E star
Oh, no, yeah.
of identity is Lagrangian
I don't know.
for any exact model category.
I don't know.
It's a natural conjecture.
Yes. Yes.
But I was looking for the.
Or rather, what are the conditions on the model category?
Yes,
which
yes.
makes
So it's Lagrangian. Yes.
makes it
I think
Lagrangian.
it's not proven.
So yeah,
Also discussed with Martin Mombelli.
Yeah.
It's the first thing.
So Lagrangian is sort of a reflection, rather indirect, but still a reflection of modular invariance of the partition function of the theory, which you can sort of natural to expect, and there would be a way to see which consistent boundary conditions in terms of these module categories. What are the conditions in the module category which will make them possible to boundary conditions? But again, it's sort of like chasing it down through algebra in indirect approach. Doing it from the conformal field theory side is probably more direct, but it's more difficult.
Okay, because we have to start soon, let's ask other questions at coffee break. Thank Alesha again. Let's resume at 11:40. We have a very short coffee break. Yeah. Yes, then you have to connect to Wi-Fi. I mean, video room is better. If you have video room, it's much better because it's not very stable. Our second speaker is